Woohoo! Welcome back. Today we're going to be talking about radioactive decay with our favorite little bacterium, berry. Yay! And before we start into the problems, I wanted to review the concept of radioactive decay, which basically means that we've got a substance which is unstable. We're pretending that berry is a radioactive substance. And so if it's unstable, then the little bits inside bonk together and then they go pa-doo, 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 and the substance itself actually shrinks. And so what does this mean? Well, it means that after a certain number of minutes or hours, seconds, nanoseconds, years, millennia, we end up with less berry. So what does that mean? Well, let's say that berry, our friend, has a half-life of 3 days. So that means that at day 0, there's all of berry. But then by day 3, we end up with only, only half of berry. And then if we wait until day 6, then we lose another half of what's left of berry. So every 3 days, half of berry disappears. Okay, so that's what half-life means. So what are we going to do to study this? Well, the great thing is that half-life is very similar to doubling time. So it turns out we can use the same basic setup for half-life. So here we go. Radioactive decay is usually modeled using half-life. Oh, berry. Oh my goodness, where'd you go? I know, that was a little traumatic. Half of berry is a very stressful concept. Okay, so radioactive decay is usually modeled using half-life. So we're going to let t equal time, just like before. Now we're using m instead of n because we're representing the mass. So instead of the number of something, we're representing a mass. You can use whatever letter you like. This is just common. M sub 0 or m naught is the initial mass of the sample, and h is the half-life of the sample. And we need to make sure that h agrees with time. So if we're measuring time in days, the half-life is in days. If time is in years, the half-life is in years. They have to agree. Okay, so we've got 2 ways to look at it. At first, this can seem really confusing, but we're just using the rules of exponents. So we take the initial mass times 1/2, because that's, instead of doubling, it's shrinking by 1/2. And then we do t divided by h, which looks a lot like the doubling time formula. Or, since 2 is just 1/2, or 1/2 is just 2 to the negative 1, we can write 1/2 as 2, but with a negative exponent. The nice thing about doing it this way is that our eyes see the minus sign right there and they think, decay, it's shrinking. So sometimes people prefer this form to this form because 1, that's a fraction, and 2, this has that minus that tips us off. Okay, so let's see what an actual problem would be like. Pardon me, Barry. So we're going to start with a heavy hitter. I'm hilarious. Polonium-210. Woohoo. Has a half-life of 140 days. So in other words, after 140 days, half of whatever you had of it is gone. It's just gone pew, 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 off into the room, gone off somewhere to find itself. So suppose a sample of this substance has a mass of 300 milligrams. So little tiny. Find a function, m of t equals m naught times 2 to the opposite of t over h, that models the mass remaining after t days. So we're going to use this formula. And we're using the 2 as the base with the negative in the exponent as opposed to using the half-life. Okay, so what is our initial mass? Our initial mass was 300 milligrams. Okay, so I'm going to have 300. And I need to make a note somewhere that I'm measuring in milligrams, because once I put the 300 in, everything else is in milligrams now. Okay, I've got times 2, and I've got the opposite of t all over 140. And here, t is in days, because 140 is in days. But that's okay, because t is in days there. So m of t is 300 times 2 to the opposite of t divided by 140. And that's it. That's all we have to do. So it's just as straightforward as doubling time, except in this case, instead of doubling, it's halving time. So it's a negative exponent. Okay, pardon me, Barry. Let's go to the next page. You guys are doing awesome. Woo! Now, what in the what? So it turns out that we can also use E to model the mass remaining after t days. And the conversion is simply that R is natural log of 2 divided by h. And right at the end of this lecture, we're going to explain why this works. But for right now, just trust me on this. We can also use m of t equals the initial mass times e to the negative RT, or the opposite of RT. And again, we know it's decay because there's a minus sign. Now, why is this useful? Well, it's useful because we've got that growth formula that is based on E. So this is going to be nice to be able to do this also in E. And so we've got these options. We could do it with a base of 2 or a base of E, which is really nice. So let's go ahead and plug in all the information. So here we're going to have to go back to the first page and remind ourselves, okay, so the initial mass was 300 milligrams, and our half-life was 140 days. Okay, so it's 300 milligrams, so we know it's 300 times E to the opposite of RT, and we know our half-life, which is our H, is 140. And so R, which was the relative growth, but now we're going to be talking about decay, right, is, and this is just a formula, natural log of 2 over H, so it's natural log of 2 over 140. And basically, I know I'm hilarious today, basically, we're just doing a change of base formula in the exponent. So this is now going to be 300 times E to the opposite of natural log of 2 all over 140 times T. So it's not as clear. It's certainly a lot more complicated than the half-life formula with the 2, but we can do this conversion, and now we've got an exponential with E, which is, again, really nice. I've got a calculator with natural log on it, and lots of other reasons. I mean, who doesn't love E, right? Euler's constant is just the bomb. Okay, so the question is, oh, and I should make a note that this is in milligrams, so I remember that, because that 300 was initially in milligrams. Okay, let's find the mass remaining after 1 year. Now, is T equal to 1? Because it's 1 year. And the answer is no. Because we've got up here, T is in days. T is in days. So T equals, and here we have our first exciting moment. Frequently, we will be told what the conversion should be. Because the problem is there aren't exactly 365 days in a year. Sometimes they're 366. Technically, it's 365 and a quarter, approximately. And so choosing how many days in a year is a little tricksy. Usually the book that you're working with or the field you're working with will have a convention, an exact value that you should use. We're just going to go ahead and use 365 for right now. And you can update that if you decide you want to try see what happens with 366. I mean, could be a fun party game, right? So T after 1 year is 365 days because already we've got T in days. So my mass at 365 is going to be equal to 300 times e to the negative natural log of 2 over 140 times 365. Oh my goodness, there's a lot going on there. So let's see if we can do this on our handy dandy calculator and make it make sense. So I've got 300. I'm going to multiply times e. And now in here, things are going to get a little jiggy. I've got to get my opposite sign. I've got my natural log of 2, close the parenthesis. I'm going to multiply times 365, and I'm going to divide by 140 and close the parentheses. And I get 49.2371665. Now, again, I didn't write how we should approximate this. I'm going to go ahead and just go to the nearest. So it's about 49 milligrams. So in 1 year, we have gone from 300 to 49. Does that make sense? And I think it does. If the halftime is 140, right up there, 140, and I'll write in here so we remember days. After 140 days, it goes from 300 down to 150, right? Because that's the half-life. It goes from half. And then after another 140 days, it goes from 150 down to 75. And that takes 280 days. But a year is more than 280 days. It's more like 365 days. So then we go even a little bit further, but not a full half-life. So slightly more than half on that third round is left. Now, what if we use this formula? So the mass at 365 days is going to be 300 times 2 to the negative 365 over 140. So we've got 300. Oop, you can't see, sorry. So this is the formula we had on the front using half-life instead of using the exponential. So 300 times 2, we're going to raise that up to the negative, you know what, I'm not sure about this calculator. So I'm realizing I feel a little bit uncomfortable. So the way I'm going to ensure that I don't have order of operation problems is I'm going to start with 2. I'm going to raise it up. I'm going to put in parentheses. So this is all going to be the exponent, negative 365 divided by 140. Close that. And then multiply by 300. And I get 49.2371665 ... Notice that we get the same result. And that's because the natural log of 2 right here with the e converts from the 2 to the e. So we can use either formula we like, whichever one we want to use to model it. Okay, so next question is, how long will it take for the sample to decay to a mass of 200 milligrams? So in other words, we want to know what is the timing if our mass is going to be 200, and we double check milligrams. Milligrams is what we were originally measuring, so we don't have to convert, which is really, really nice. Okay, so I'm going to go ahead and use the exponential form with e. M of t equals 300 e to the opposite of natural log of 2 over 140 times t. And I want to know when that's going to be equal to 200. Okay, so what's the first step? The first step is to get rid of this 300 by dividing both sides by 300. Now, this is going to be kind of awkward because this is not a nice number. And here we're going to run into some problems. If I convert this to a decimal right now, it will be an approximation. And then everything else I do will be a little bit off. So instead, I'm simply going to write it as 2/3, and I'm going to leave the calculation to the very end. So I've got e to the negative natural log of 2 all over 140 times t equals 2/3. Next thing I'm going to do is I'm going to take the natural log of both sides, because that's what the book likes to do. You can also convert it to exponential form if you prefer. Okay, let me get some scratch paper. We need some scratch paper. Come here. Okay. Woohoo. Oh, my hands are tired. Are your hands tired? Hopefully you're having a great day and your hands are not too tired. But I have to admit, sometimes all this writing, my hands are just like, no, let's not do this. Let's go outside and play. Okay. And unfortunately, of course, Berry Bacteria is here going, yeah, let's go play in the dirt and not wash up afterwards. That sounds great. Okay, so I get the opposite of natural log of 2 all over 140t equals the natural log of 2/3. At which point, you'd be forgiven if you look at that and go, yeah, this is exactly what I didn't want to have to do in math. And the answer is, yeah, I know. So what do? Well, we want to find t. Remember that what we're looking for is t. So I'm going to multiply both sides by 140 so that I get the opposite of natural log of 2 times t equals 140 times the natural log of 2/3. So I got that 140 out of the denominator. And then I'm going to divide both sides by the opposite of natural log of 2. Yeah, it's not... I mean, maybe it is a party. Maybe y'all are like, woohoo, this is the best. I'm not sure I think this is a party, but hopefully if you take a look at this, you see t. I know there's a lot going on, but basically we've got a negative natural log of 2 on top and a 140 on the bottom. So I multiply both sides by 140, and then I divide both sides by the opposite of natural log of 2, and that's how I crack open t. Whenever you want to get t out of an exponent, you're going to use logarithms, and you're going to have to multiply and divide like this. Okay, let us see. So are there any guesses? Let's think about this again. What was the question? We want to go from 300 down to 200. Now, half-life would mean we go from 300 all the way down to 150. So this isn't a full half-life. So it should be less than, right? What's the half-life? Where was the half-life? 140 days. So it's less than 140 days. So let's see what we see here. Clear this out. 140 times natural log of 2 divided by 3. See, I'm not entering 0.6. I'm entering the full expression. I'm going to let the calculator take control of how it's going to round things. That way, it will do a better job than I would just writing it down on the piece of paper. Okay, so I got that. Now you can see that I've got that negative, so we don't have to worry about the negative because I'm going to divide out. I'm going to divide that by the opposite of, oh, you know what? I don't trust this calculator, so I'm going to divide by, and I'm going to put parentheses in, the opposite of natural log of 2. Close parentheses for natural log, close parentheses for the outside, and I hit enter, and I get 81.89475 and some other stuff. So it'll take about 82. We have to remember what we're measuring in. We're measuring in days. So 82 days, not quite a full half-life of 140, before it goes from 300 milligrams to 200 milligrams. Woohoo! You having fun? Yeah, we're having fun. This is a good time. I know, mathematicians know how to have a good time. Wait till you see what comes next. Now, this is where the party gets started right now. Okay, so the question is, in part B of this problem, we use the fact that we can convert a half-life formula into a percentage decay formula by calculating that natural log of 2 over h. Why does this work? Now, I didn't want to take too much time, so I wrote down most of this, so you don't have to, wait for me to write it all out. So here's the half-life model. Here's the radioactive decay in terms of E. So here's in terms of 2, here's in terms of E. And we're going to set them equal, right? Let's compare the two. And what I do is I divide both sides by the initial mass, so it cancels out. So I end up with 2 to the negative T over H equal to E to the negative R over T. And so what's suggested is that we should take the natural log of both sides. So let's take the natural log of both sides. Natural log of 2 to the opposite of T over H equals natural log of E to the opposite of R over T. Now remember what happens with logs. Logs mean that exponents come flying down in front. So I get the opposite of T over H times natural log of 2 equals the opposite of R over T. Oh my goodness. You guys probably saw this happening. I did not. We can't have a party if you put T in the wrong place, huh? So where should the T be? I copied it down incorrectly and just ran with it. So it's the opposite of R times T. I'm so sorry to be confusing. So here we've got the opposite of T over H, and over here on the right, the opposite of R over T. So the opposite of T over H on the left, the opposite of R T on the right, I get the opposite of RT times natural log of E. Natural log of E is 1. So I get the opposite of T over H times natural log of 2 equals the opposite of RT. So what can I do? And what are we supposed to be doing? I want to find out what R is. So I want to solve for R. So I'm going to multiply both sides by a -1. And then I get T over H times natural log of 2 equals the opposite of R, positive RT. Oh my goodness. Oh my goodness. It's such a party, I can't even keep track of my numbers. Okay. Notice that I got an H in the denominator. I'm going to write this slightly differently. I'm going to write it as T natural log of 2 over H, totally allowed to do that, equals T times R. And I'm going to divide both sides by time. If I cancel out time on the left, I get natural log of 2 over H. If I cancel out time on the right, I I get just R. And that's my formula. To convert from half-life model to radioactive decay model, they're describing the same situation, just with different bases. This is our change of base for this formula. Okay, you guys have made it through yet another long video. You're amazing. Kiss yourself on the brain. Congratulate yourself for being amazing. And know that I'm really proud of you. And I think you're amazing and incredible. And I give you all the woohoos. And I wish you all the happy days and all the lovely, lovely moments of math. And hope you can math on. Woohoo.